Right, here we go. This talk will be on the subject of molecular dynamic simulation and finite element modeling in simulating the mechanical properties of cross-linked polyethylene. And really the presenters are myself. My name is Jukka Vaari. And then the second half of this presentation will be given by my colleague Viacheslav Balobanov. And as said, this presentation will give you a short introduction to the modeling tools for simulating the mechanical properties of cables as a function of aging using the techniques of molecular dynamic simulations and finite element simulations. Okay. If we start right from the basics, then what is molecular dynamics? It's simply a technique for computing the movement of atoms or molecules using classical equations of motion. So basically we are solving the Newton's second equation, force equals mass times acceleration. And this is really conceptually very simple. So we are taking a group of atoms and we are not solving the Schrödinger equation for those atoms. I will leave that to Guido Roma, he will do that. But instead we are using a very, very simple approximation of Schrödinger's equation. We are replacing that with simple analytical expressions. So what we are doing in molecular dynamics, we are saying that our atoms, they are simply points in space that have one property called mass. And we put those atoms somewhere in the space, and then we define between those atoms, we define an interaction potential, V, from which we then can compute the forces that are acting in between those particles. And once we have the force, we can calculate the acceleration. And once we have the acceleration, we can then move these atoms from one position to another. And we repeat this very simple loop until we observe something interesting, or then we don't. So really, it sounds very simple, but this is computationally actually quite heavy because of the sheer number of atoms that we need to, for example, measure mechanical properties of a material in a sort of sensible way. So the main computational effort comes from the big number of particles that we need to use in our computations. And for example, the polyethylene samples that I have been using, or the models I have been using in this work, contain like 300,000 particles. Okay, it's quite important to understand where we are sitting now, both in terms of physical length scales and physical time scales. And here are basically all the scales of materials modeling, if you will. In the next talk, Guido will remain in the quantum scale. In this presentation with molecular dynamics, we are in what this picture calls the atomistic scale. And maybe I should simply put on the presenter mode. Yeah, the atomistic scale, and really the numbers that we need to remember are that we are, in terms of length, physical length, we are in the let's say nanometer scale, not more, in the nanometer scale. And with respect to time, we are somewhere in between nanoseconds and microseconds. Typically, some of the simulations I have conducted in this work, they have a physical time duration of a couple of microseconds. For molecular dynamics, that's quite a lot already. So these two numbers are really important to be understood with respect to what I'm saying in this presentation. Okay, I said that the atoms in molecular dynamics are just points in space. So how do we make molecules out of those atoms. And that's done by defining this interaction potential between the particles in a smart way. And we are speaking of bonded and non-bonded interactions between the particles. If we are looking at for example, this picture A here. Here we are defining a force between two particles that looks like a harmonic spring. This is really the potential energy of a harmonic spring. And this is a simple but very often used way of defining a chemical bond in these molecular dynamic simulations. But that's not enough. We have to do something more in order to define meaningful polymer molecules. And the next thing, if we have a set of three particles, we have to define an angle that these three particles are forming. And again, a very, very often used approximation is again the harmonic approximation for the bond angle potential energy. So that's for the bond angles. But then this third bonded term is about sets of four particles. Now, three particles always sit in a plane, but the fourth particle may not be in the same plane as the other three. If it's not, then it's because this bond between the J and K particles has rotated. And we call that bond rotation or bond torsion. And that has a slightly more complicated mathematical form. But this torsion potential is actually hugely important when we are talking about polymers, and I will show more on this on the next slide. The non-bonded interactions are typically the van der Waals interaction due to the polarization of the molecules, and then the electrostatic potential, because even if our molecules are electrically neutral, on the whole, the atoms of that molecule may still have some non-zero partial charges associated with them. So this is the set of terms that an interaction potential in a classical molecular dynamic simulation typically contains. Okay, now that we can build polymers, or I promised rather to say something on the importance of the bond rotation or the torsion term. If we have a chain of these chemical bonds and the associated bond angles and the torsion terms, this will result in a chain that is not straight, but it goes like this. It wiggles around in space. It has many bends and so forth. And that's because of the torsional term. And this physical shape of a chain is very important. This is what actually defines many of the mechanical properties of the material, because if you don't see it from one chain, but imagine you have many chains, then these chains become entangled with each other. And the fishing analog on the right is just an example showing how one very long chain can get entangled. So imagine if you have many long chains, you can get very, very sort of mechanically tight entanglements with long polymer chains. But this is all because of the wiggling and non-linear shape of these polymer molecules in the material. So when these molecular chains go around each other, we call it an entanglement, but they may also be chemically sort of connected to each other. So by chemical bonds, and then we call it the crosslink, and maybe the fishing net would be a more appropriate analog for that. So these entanglements and crosslinks, they are very important with respect to the mechanical properties, and we have to sort of be able to model those accurately. Now, a polymer is a long chain, and if we include all the atoms in our description of the molecule, then we have a lot of atoms. And when we have a lot of atoms, we have to compute these forces and interactions many times, making the simulation very computationally expensive. So one way of reducing that computational complexity is actually to take a monomer from the polymer and represent it with one simple larger particles. And if we do that, if we then define the interaction potentials between these blue spheres instead of all the small spheres, we call this coarse graining, and we call them the potentials, we call them coarse grained potentials. This is one standard trick that is often used in molecular dynamics modeling of polymers, simply to make the computations slightly less expensive computationally. And we have also done something like this in our work. Okay, now like we do in real life, before we can study material, we have to manufacture the material. And that's what we also do when we are modeling the material. We have to make the material first. This is sort of our digital polyethylene factory, if you will. And the process goes more or less like this. In the first stage, this is where we put the atoms, we choose what kind of particles we use to describe the polymer. Do we explicitly include all carbons and all hydrogens into our molecules? Or do we make this coarse graining trick and we take one monomer out of the polymer and say that this is particle, this is a united atom particle or a coarse grained particle or whatever. And that's what we did in this work. For each carbon and 2 hydrogens, the CH2 unit, we defined that this is a one united atom, and we represented our polymer entirely in terms of these united atoms. And then we chose an appropriate force field or interaction potential that then creates the forces between these united atoms. So that's stage one. We have to choose how we describe the particles. And the second stage is then generating the actual structure. Like in many simulations, we have an empty simulation box that we have to fill first. So we have to choose the number of chains that we use to describe the material. And typically this would be, in our work, this has been like 1,000 chains or something like that. We have to decide whether all of those chains are of equal length, or do we have a more realistic chain length distribution? And in our case, we have used polydisperse systems with the dispersity of 2. Once we have those chains, once we decide the number of chains and the molecular weight distribution, we have to use a code, either a commercial code or we write a script of our own to pack those chains into the simulation box. Just put them in some initial places in the box. We don't expect that to be a thermodynamic equilibrium configuration, but we have to start from somewhere. And once we do that, we then actually run the molecular dynamics simulation, and we do it so long that we get really an equilibrium configuration, and we have to actually measure some of the properties of those molecules during the simulation to be sure that we have reached equilibrium. We have to measure like the shape of each of these chains. We have to measure the distance between the ends of the chains, and there are many parameters we can measure during the simulation to ensure that we have really reached some sort of an equilibrium. Typically, we do this in the melt state, so we are above the melting temperature. And when we have an equilibrium melt, then we decide if we are modeling a cross-linked material. If we are, like in this case, we are building additional chemical bonds between the chains. These are the cross-links. And that's really a fairly simple technical trick to do, just changing the bond topology in the model between particles that are sufficiently close to each other. No big deal, easily done, and you can control the gel fraction of the material quite easily. So once you have that, the fourth step is then the crystallization. We are studying a semi-crystalline material, so we have to have some crystallites in the model. And this we do by cooling the system far below the melting point. And now this is one of the limitations of the molecular dynamics technique. So we have to create those crystals very fast. We don't have hours or minutes or anything like that to do the actual crystallization like would be done in real life. We have only a couple of microseconds to do this whole thing. And that's why we have to cool the system far below the melting point to create those crystals quickly. It's a limitation of the technique, and the resulting structure is not quite realistic. We don't have these nice crystalline lamella and stuff like that. We have these smaller crystallites, but we hope that anyway this will provide us a structure that we can meaningfully use to extract some mechanical properties from the material. Okay, so far we have created fresh cross-linked semi-crystalline polyethylene. But this project was also about aging and the effects of aging on the mechanical properties of these materials. So how do we introduce the effects of aging to the material? Now this morning we heard a talk on the kinetic modeling of aging. And we have this oxidative degradation scheme that results, among other things, in breaking of chemical bonds. We have bond scissions, and we also may have crosslinks. But often in the kind of aging experiments that we have conducted in the Team Capitals project, the chain scissions are the dominating thing. So in our modeling work, we have so far only considered the bond scissions due to aging. In the middle part, you see really the result of a crystallization simulation. The red curve up from 0 to 2 microseconds. That's when we crystallize the fresh material. And we can see that the cross-linked material with a gel fraction of 0.71 reached a crystallinity of about 40%. Now at this point, at this dashed line, we now introduce the aging effects. We get an estimate on the chain scissions in the material due to aging from the kinetic model. A few percent of the bonds will be destroyed by aging. That's the message from the kinetic modeling. So we can do that thing here. We can cut a certain fraction of all the chemical bonds at this point, and then we can continue the crystallization simulation. If we do that, we notice that the crystallinity increases due to aging, which is also, by the way, an effect that we have measured experimentally in this project. So we see really this effect of increased crystallinity. Due to aging, we call it chemicrystallization. And why does that happen? When we break a chemical bond, it means that the chains become shorter. And when the chains become shorter, they move more easily back and forth in the material, so their mobility increases. Now they are mobile, more mobile. But when a chain sits in the crystalline phase, it's a thermodynamically more favorable position. So if this increased mobility allows the chains to move from the amorphous phase to the crystalline phase, it's energetically a favorable thing. And that's the third thermodynamical reason for why the crystallinity really increases. And this is an effect we see both experimentally, and we are able to capture that in our simulations. And now we are in the position to see whether we can actually extract some mechanical properties out of these simulations. And how do we do that? The answer is we do it almost in the same way as we would do in real life. The pictures on the left are really pictures of a tensile test apparatus. We have this dumbbell-shaped sample which we clamp into the machine and we stretch it, and then we observe a strain-stress dependence, a stress strain curve. with the MD, we do the same thing. We start from the initial cubicle simulation box, and we introduce a deformation for that box. We deform the box more and more. This will result in rearrangement of the chains. They try to get more straight. Remember that they were coiled when they were in an equilibrium, but now we are pulling them straight. That's not an energetically favorable thing for them to do. They want to return back to the coiled conformation, and that's really the micromechanical reason for the force that we observe in the tensile test. So we achieve the strain by deforming the simulation box. But here is an important limitation, again from the molecular dynamics. We have to do this in a couple of microseconds. So we have to achieve a large strain in just a couple of microseconds. It means that our strain rates are far, far greater than you would have in a real tensile test. We are like easily 8 or 9 orders of magnitude faster than in real life. And that will inevitably have some effect on the results that we observe. But never mind, we shall do that. So the stress tensor is computed from the simulation, and it's a straightforward thing to do to obtain the stress strain curve. We observe that the simulated stress levels are sensitive to the selected force field and the very, very high strain rate that we are forced to use. And we can also observe the evolution of crystallinity, chain orientations, chain entanglements, and so forth during the pulling of this simulation box. One thing we are sadly missing from our simulations, and we don't have a proper explanation for that yet, is that the actual breaking of the material, like happens in this picture, it's difficult to observe in the MD simulations, and we are not really sort of satisfactorily able to explain why this is. But the elongation at break is one parameter we hoped to get from these simulations, but we couldn't. But what we get are some sort of stress strain curves. On the left, we have an example of a molecular dynamic simulation, and on the right, an example of real experimental tensile test data from this project. And we see that the agreement is it's qualitatively good, and it's also quantitatively pretty good. What we see on the left-hand side, there are two materials that we are comparing. The red curve is the cross-linked polyethylene, and the blue one is linear polyethylene. And we see that actually the difference between those materials becomes apparent only at very, very large deformations. So this is the effect of the actual cross-links in the material. The rest is actually entanglements. So the conclusion more or less from this is that the entanglements between polymers are dominating the mechanical behavior of the material. There is a set of stress strain curves for the material. For the cross-linked material, the red curve is for the fresh material, and the rest of the curves are for different amounts of aging introduced to the material. And on the left-hand side, you have the logarithmic presentation, and on the right-hand side, you have maybe the more familiar engineering picture. And there are three things we should observe. The first thing is that the initial slope of these curves in the engineering presentation, this initial slope is increasing due to the aging. That means that the Young's modulus of the materials is increasing due to aging, which we can then attribute to the increased amount of crystallinity in the material. The second thing we observe that the yield stress is also increasing as a function of aging, and that's due to the thickening of these small crystallites that we have in our model. And the third thing is that the strain hardening behavior is changing. So we have, once we introduce the aging to the material, there is less and less strain hardening in this material. And these are some of the issues that then can be transferred from the molecular dynamic simulation to the finite element simulation. And I believe this is a good point now to give the microphone to my colleague Viacheslav, who continues to talk about the the finite element modeling, and I guess I can show the slides if you do the talking. So please.
Yep. Okay. Good afternoon, dear audience. Yeah, I'm going to show some slides about finite element simulations and how finite element simulations use experimental data and why experimental data is important for numerical simulations. And yeah, for this, I will use the results obtained in this Team Cables project. So on the left of this slide, you can see the tensile curves obtained, stress strain curves obtained in experiments. So we have several specimens, and we are doing some procedure of averaging to get one stress strain curve to use it in further simulations usually. But it's important to properly process the experimental data before we will use it in our simulations. So different interpretations of this data and initial parameters which we assume can affect the results drastically. And on the right side of the slide, you can see three curves. So green and orange lines are about the same stress strain curve, but we just assume different initial length of our specimen. So once we are using these dumbbell specimens, we can put, for example, distance between grips in the testing machine as initial length, and it's green line here, so it's 50 millimeters, or we can just consider gauge length, which is actual deforming part of the specimen, and you can see how different the results are. So we need to pay attention to this a lot and interpret the results properly. And also the blue line here is probably the most exact, because for this we used video analysis, meaning that you can see on the left bottom side of the slide some screenshots from video analysis. So in principle, we put some dots on the specimen and then take the whole tensile process on camera. And then by image analysis, we can subtract stress strain curve from there by measuring the distances between these deformed dots. So this is probably the most exact way to get stress strain curves, stress strain data. And yeah, the problem is that we need to do a lot of additional work. We cannot just use data from the machine, but also need to take the videos and then apply some programs to analyze the actual results. Yeah, next slide, please. So once we have the results of experimental results, and we have this stress strain curve, and we decide what data should we use and how to process it. To use this data further in finite element simulations, we need to decide which material model we are using. And here different approaches can be applied. 1 and 2, you can see here, are two approaches we are using for this project, but of course many different material models can be used as well, which one assume appropriate. And first way we used is just simple elasto-plastic model. So we simply analyze the the stress strain curves and extract elastic and plastic data from it. So elasticity usually, it's simple isotropic elasticity, and it usually means Young's modulus and Poisson ratio. And then for plasticity, we just take a table of stress and strain values and use them directly in our calculations. It's easy, but the problem of this approach is that if we have not simple tensile experiments, we will probably have some problems with our with exactness of the results. So probably some more sophisticated models should be used if we have complex stress strain state in our material. For example, as in composite material, we have polymer metrics and alumina inclusions. And if we consider polymer stress strain state in the polymer metrics will not be just uniform tension, but it can be much more difficult. There are some tensions and compressions in different directions, even though we only apply tensile loadings because of the complex geometry of the specimen, I mean microgeometry. The state will be complex, and it's not sufficient probably to use simplest models, so we need to consider something more complex. And for example, here you can see the elasto-viscoplastic phenomenological model which we used. And on the next slide, I will explain a bit more about this model. So the idea here is to use phenomenological approach. So we know that in the beginning of the deformation of the material, we have elastic area, elastic regime, where we apply some forces, and there is no permanent deformations in the material, no plastic deformations when we remove the external loading. Then we go to crystalline or intermolecular phase, which is actually viscoplastic. Then some entangled polymer flow, so meaning that we go to polymer chains interactions, and then once chains are starting to align, we have this strain hardening. So as you can see, the model can explain the stress strain behavior of the material phenomenologically. So we know what is happening inside the material, and we apply this knowledge, and we obtain the behavior of the material. This approach is much more complex than just using some results directly from the experiments. So we need to know the model, we need to know how the parameters affects on the behavior of the material, and we need to properly fit all the materials, and experimental data will help us here. Yeah, next slide, please.
Sorry, I interrupt you just to say that you have 5 minutes left.
Okay, cool. Yeah, so before I mentioned only stress strain curves and elasticity and plasticity, but to model the polymer properly, we also need to introduce some damage and aging. And yeah, and once we have these experimental data with different doses, irradiation doses, we know elongation at breaks, and we know how these irradiation doses affect the elasticity and plasticity behavior of the material. So we actually can use this data further for our simulations. So we directly extract the Young's modulus from there, some plasticity properties, and also we use this ductile damage criteria. So you can see on the bottom of the slide this set of curves. So this is actually criteria for damage and how it changes with aging. So yeah, next slide, please. Probably I will not pay attention a lot to the damage model itself. And so yeah, let's go directly to the next slide, to the actual micromodel we are using for the simulations. So it is a representative volume element, so meaning that it's a cubic piece of the material which is like representative enough to model the bulk composite material. It consists on the polymer matrix material and alumina particles. For here we assume that alumina is stiff enough and it's much stiffer than the polymer. So we just apply some simplest model for it because there is almost no deformations in the particles, but we use this complex model for polymer because everything interesting is happening only in the matrix and between the filler. And so I mentioned the stress-strain behavior damage, and also it's very important to properly model the interface, debonding, and other things which can happen on the boundary between the particles and the matrix. So next slide, please. So once we have everything here, meaning geometry of the model, matrix material damage and interaction properties and stuff, all this stuff, our model is ready and we can validate it with the experimental results. On the right part of this slide, you can see how the visual comparison can be used for like checking if our debonding process is happening properly. So we just compare on FIB-SEM images with our model and can see that okay, at least it works in right way. And other way to check it is just of course, measure the elongation at break and compare how elongation at break changes with aging and how the simulation can reproduce this. Yep, next slide, please. And once we have our micromodel working properly, we want to do some upscaling to model some real piece of the material. So we can go here in at least two different ways. So if we can do like procedure of proper numerical homogenization, solve some set of problems, numerical problems, and from the materials with complex microstructure, we go just to simple homogeneous material, and its properties can be used directly. After that, the properties can be used for modeling some dog bone dumbbell specimen tension in simulations or some real cables, for example. Or we can go in another way just by using the stress-strain curves directly from microstructure to macrostructures. It's also a way, but probably not suitable for every problem. Yeah, next slide is about summary. As we can see, MD simulations give qualitatively correct shape for stress-strain curves, even though we have some limitations, as Jukka explained to us. And this, how can we use these simulations in our studies? So how we can see how different changes in microstructure and molecular structure, like transitions, molecular weight, or chemicrystallization can be used and how they affect the mechanical behavior of the material. And in an ideal world, we can use this data directly for finite element simulations because it's fully rely on experimental data usually. And so we need to know how to fit our material models. And we need to pay attention to proper interpretation of these data because it can affect our results drastically. Choose right proper material model and do the correct parametrization. And we need in this project, the important parts of the model are interactions between matrix and fillers, also damage initiation and propagation models. They were taken into account, but of course the list is not limited only by these parts of the models. And we always have possibility to upscale from macro level to macro level to simulate the real life problems. Yeah, thank you for your attention.
Thank you. So thank you both for your presentation. So now it's time for questions. Also from online, obviously, if they want. Yeah, sure.
So Maxime Lacuve from Nexans Group. I have a question concerning molecular dynamic simulation. How do you distinguish physical entrainment to chemical entrainment? Is it possible to distinguish that? And my second question is, how do you simulate the interface between crystalline and amorphous phases?
So the first question was about
how do you simulate how do you distinguish physical cross-linking to chemical cross-linking? Is it possible to distinguish?
yes, well, what we do in the simulation, we define these chemical bonds when we are introducing the chemical crosslinks. So that really ties the chains tightly together. So that doesn't allow the relative movement of the chains with respect to each other. But if we have this entanglement, then the chains can actually move around each other. It's sort of implicitly taken into account by the model. And much the same way regarding the second question, we don't have a separate interface model in the molecular dynamics model. We just have chains that are either part of the crystal or part of the amorphous phase. These chains can sort of come out of the crystalline phase and make turns in the amorphous phase and then enter the next crystallite. So it's something, the interface is just something that is formed during the simulation, but there is no specific model for the interface as you would need in the finite element simulation.
Okay, and so in your simulation box, how many atoms?
These were the united atoms. So these were the particles representing 1 carbon and 2 hydrogens. And in my simulations, I typically used 300,000 of these particles.
Okay, thanks.
Thank you. Is there any other question? No, I actually have one. Hello. In your slide, you suggested that you remove the contribution of alumina because it does not deform, obviously, during the measurement. But how do you, because we have seen, for example, from experimental data, that if we have ATH inside the polymer, you will have an elongational break that is way lower than the polymer without ATH. Is it possible to simulate the contribution, the interaction between the ATH and the main polymer matrix in terms of mechanical properties?
Well, probably I was not exact saying that. So actually, we take into account, of course, the particles. I just wanted to say that the particles themselves are not have complex material model. It's just a simple elasto-plastic model. But of course, the main goal of all these simulations is to see how different amount of particles affect the behavior of the material, how the shape of the particles can affect, how the material of the particles can affect, and how the interface can affect the behavior of the material.
Okay. So it is possible to simulate this.
Yeah, definitely. We are doing this actually.
Okay.